Okay, so this morning, looking at linear approximation, differentials, and error. So, linear approximation is actually something we've done a bit of already. This is more applying the idea outright and in its own kind of section here. And then we'll look at differentials because this whole concept lends itself to this smaller idea that's pretty interesting, kind of a bit of a hot topic in the math community amongst the super nerds, but we don't have to go too deep into that. But linear approximation and linearization, again, I feel like math terms kind of fly over our heads sometimes, but they're really descriptive in what they do. Linear approximation, what is that telling us? We're approximating something with a linear function, okay? Or linearization means turning something into a line, okay? Why would we want to do this? Well, the reason that we'd want to do this is because lines are simple, right? They're simple in a bunch of ways. They're simple because all you need to describe a line is a point and then the slope, right? You need to know the delta y over delta x. That tells you all the characteristics about a line. And then you can predict what points will arrive on, any part of this rule. Not many things are actually linear in the real world, but what we know is that when we zoom in on functions near a certain point, we zoom in far enough, they start to look linear, right? And they sort of act linear in that range if they're differentiable, if they're nice, if they're smooth and continuous. So, what that allows us to get away with is saying, well, instead of having this long, complicated formula for a function's output or that function's derivative's output or whatever it might be, we can use a line instead. And this helps us save things like computation time, which is a big consideration, and and also just to hand this off to non-experts uh, and make it something that's usable, right? Are you really going to be making a certain item at the extreme levels of this material, or are you really going to be staying within this range? We can just give you this linear formula instead of this really complicated kind of back of the house type of science. So simplifying things is very important. We work with approximations all the time. Let's jump right into some things we'll want to recall in order to kind of refresh our memory, and then we'll look at some applications. So the first thing we'll want for this application is to remember the equation for the tangent line. So here we'll use what's called point slope form, where you can see the x coordinate that the function is going through as well as the y coordinate. So here's the x coordinate a, and here's the y coordinate f of a. So what this does is gives you the equation with the slope of the tangent line here. So obviously you need to know the derivative of the function f of x in order to get this tangent line. That's usually the hardest part of finding the equation for the tangent line. All right, it's the only thing that you really probably don't have. So this is the equation for the tangent line, but what we can also do is take this one step further and solve for f of x by adding f of a to both sides. Okay, and so the idea here is that f of x, the function, at this point x equals a, is equal to what's happening on the right-hand side. And we also know that since this is the slope of the tangent line, this is taking on the rate of change of this function at this point. So let me give us a little visual here. I'm a visual guy. If I've got some random function f of x, I've got some point that I'm interested in, x equals a. Let's say the tangent line is doing something like this. We'll call this L. This here is telling us that within this region, right, if I were to zoom in really close here, these two curves would be indistinguishable from each other. Right? The tangent line L would be, very, very close to f of x, almost indistinguishable. I'm kind of drawing them a little bit apart so we can see. But if we get zoom in close enough, they'd really be laying right on top of each other. And so what's a better approximation for something that a function that's laying literally on top of the curve that we care about in that region? So when we say linearization, this is what we're talking about. This is meaning zooming in enough that the tangent line can effectively replace the function. And effectively replace, meaning in an applied context, right? There's mathematical situations where they're not really equal, but they are very, very close. So what we say is that, near x equals a, f of x is approximately f of a plus f prime of a times x minus a. And sometimes we'd give this function its own name. We might say that this is equal to L of x, and this is also what's called linearization, coming up with an L of x function, meaning just what's on the right over here. We'd call this the linearization of f of x. So we're zooming in far enough. So near x equals a, you might be saying, like, what's near, Mally? What's close to that? Essentially very, very close. Well, it depends on the context, but not very far away from a certain point does this break down. But we zoom in far enough that the tangent line can effectively replace the function. So we could say, for a very small range around this point, this line is a great replacement for the function f. And again, the idea here is that this would be a formula you'd hand off to somebody who's working in the field. They don't need to know all those, back end details. So I think another point of confusion is when we're always working in the abstract with variable names and things. So let's do a quick example and I'll show you how this looks. So let's assume that the square root function is too complicated for our scientists or for our techs out in the field. And so we need to come up with a simpler way to approximate the square root of 9.05 is the goal. We have this function. This is too complicated to work with. We're interested at this certain value, a equals 7. You'll always be centered somewhere when you're doing a linearization. Because as you see up here, this tangent line is not good to approximate what's happening to the function here, right? This doesn't represent the rate of change or the values that is happening at this a or at this a. Okay, so we'll always be given an a value. And so we want to use it to approximate the square root of 9.05. And then we'll see, is this an overestimate or underestimate? So let's go ahead and find the linearization. Well, the linearization, we can say L of x is equal to f of a plus f prime of a times x minus a. And we know that our a is 7, so we can go ahead and substitute that in here. Because again, what is this getting us? This is getting us the equation of this line, this tangent line, through the point that we care about on the function's curve, f of x, the square root of x plus 2. So we're just looking now to find these values that we don't have. So what is f of 7? Well, f of 7, let's do some side work over here. F of 7 is the square root of 7 plus 2, which is the square root of 9, which is 3. So this becomes 3 plus, and then we need f prime of 7. So we need the derivative here. And so this is what we're going to probably take the most time to do. F prime of x is what we'll need first. So this is really the derivative of x plus 2 to the 1/2 power. Remember that very helpful way to rewrite roots. It's using rational exponents. So the derivative of x plus 2 to the 1/2 is 1/2 x plus 2 to the negative 1/2. Don't need the chain rule here because the derivative of the inside is really just 1, right? But you can write it there if you're, kind of still learning the chain rule and need to be super comfortable with that. So then if this is f prime of x, then f prime of 7 is 1/2 of 7 plus 2 to the negative 1/2, which is 1/2 times 9 to the negative 1/2. And what's 9 to the negative 1/2? This is really 1 over the square root of 9, which is really just 1 over 3. So this whole thing is 1/2 times the third, which is 1/6. Oops. There you go. So these two values that we went looking for, 3 plus 1/6, we now have. So now we have a function of x, what we call the linearization of the function f of x at a equals 7. Okay, so what again does this mean? This means that my square root function is doing something like this. This is close to how it looks, square root of x plus 2. And at a equals 7, we wanted to get an equation for the tangent line, the line that acts just like this function in a close range. And so what this function is here, this is our L of x. This is the equation of this line. It's got the slope of the curve because it's got the slope of the tangent line, and it's placed correctly in space with these x and y coordinates. All right. So I'm trying to cover the basics very strongly so that we can move on and feel confident. So that's the linearization. Use it to approximate 9.05 is what we're being asked to do now. So square root of 9.05, we're not going to use the original function. We're going to use our linearization to predict the square root of 9.05. So what would the square root of 9.05 be? Well, this would be like L of 7.05, right? Why? Because, well, L of x was trying to predict what happens near a equals 7, right, or x equals 7. And so to predict the square root of 9.05 would really be like x plus 2 equals the square root of 9.05. If we went to go solve for what x value this is at, this would tell us that x is really at 7.05. So we're using the linearization to predict what happens at x equals 7.05. So I hope that makes sense. Again, you can pause and go back to make sure. But in any event, we need the linearization at this 7.05 value. So we'll just plug this into the equation that we got, which is 3 plus 1/6 times 7.05, plugging in for x, minus 7. All right, and after we throw this in our calculator, we get this is around 3.00833, repeating. And so this is our approximation for the square root of 9.05. And this should seem pretty reasonable because we know the square root of 9 is 3, right? So a little bit higher than 9 makes a little bit of sense. But if you can also, test what the calculator would come up with by just taking the square root and see if this is reasonable. And then, so that's not too bad. And then the second question is this an overestimate or an underestimate? So you got to ask yourself, how would I know this? So there's two ways. One would be to do what I did, which is give yourself a quick sketch or maybe graph the function. You're going to see that this function is concave down. You're like, Mally, why does it matter that the function's concave down? Well, if a function is concave down, and then I draw some tangent line to it, notice what's happening with these values. All these values are overestimating. Everything that sits on this line, except for the point at x equals a, all these points are higher than the curve. And just the opposite would be the case if it were concave up, right? So, or also called convex. So if it were convex, you notice that actually the tangent line is underestimating all of these values. So if you take a look at your curve and you see, well, this is concave down, then my tangent line will be overestimating. So you can be confident that this is an overestimate since f of x is concave down here. Now this function's concave down everywhere, but we know that there are functions where that's not the case, and we just need to be worried about the neighborhood we're in. So this is a just quick, very common example of how to use linearization on the square root function. All right, and this one I think is a cooler example because it's a little more realistic. You know, you don't have many people asking for simplifications of square roots these days, even though that used to be a big thing because we didn't have calculators not that long ago. But here we have a model given for the speed of sound in dry air. So this would be of interest to, you know, probably aeronautical engineers and what audio engineers. So f of t equals 331.3 times the square root of 1 plus t over 273.15 meters per second, where t is the temperature, right? So sound is moving through the medium of air, and the temperature affects the density of the air. So these things are not linearly related. And so but we want to find a linear function that approximates the speed near 0 degrees Celsius. So let's say we're at a place where it's a stable 0 degrees. You know, we want something that gives us a good rule of thumb, a good approximation for the speed of sound in that area. We don't need to hand off this more complicated formula to people to do their work. So again, what is the linearization? Linearization, well, this will be of t. It's going to be f of a plus f prime of a at t minus a. And so again, the hard part is usually coming up with this piece, right? It means that you need to take the derivative. It means that you need to evaluate that at that certain point. These pieces here and here are usually quite simple to find. So let's go ahead and find f prime of t then. F prime of t is, well, we know we've got to take the derivative here of 331.3 times the square root. So I'm going to write this again in that helpful way of 1 plus t over 273.15 all to the 1/2. And then again, this is a scalar, so this just hangs out front, 0.3 times, and then the derivative of this piece on the right, 1/2 times 1 plus t over 273.15 to the minus 1/2. And we do need to use the chain rule here because the input, this t value, is being scaled by this number. And again, you know, this is, this is t over 273.15 is really equal to, you know, 1 over 273.15 times t. This is usually, we're not that comfortable with fractions. This is usually a place of breakdown. So what is scaling the t? It's this scalar of 1 over 273.15. So when we use the power rule on this inner piece, this is what we'll be left with for that inner derivative. Okay, so this is the chain rule here. And so now we can do some simplification. So I'm going to combine this, and this. And so that works out to be, excuse my voice, this works out to be 0.60644 all times 1 plus t over 273.15 to the minus 1/2. I would leave it like this, honestly, but you can write it like this if you want. Or you can get the decimal into exact form. So either or. But I would leave it like this. This is my f prime of t. This is not our final answer. What are we after? We're after the linearization. We're after a linear function. This is my derivative, though. And what do I need? I need f prime of 0, right? That was kind of our whole goal here. So we found f prime of t. So now I can find f prime of 0, hopefully pretty easily. It's 0.60644 times 1, 1 plus 0 over 273 is just 0 to the minus 1/2. And so that is really 1 to the anything power is just itself. So what we're really getting is this 0.60644 is the slope of the tangent line at this point. And so we've got that. We've got now, we need f of 0. Plug this on in to be just super clear for these first examples. And so f of 0 we know is going to be just 331.3 plus f prime is 0.60644 times t minus 0, so that's just t. So this is our linearization of t. And so here what we have is a linear function that represents this function f of t near t equals 0. So I'm going to graph these real quick and show you just to have a not hand-drawn visual to help you solidify this idea. Okay, so what I've done here is plugged in my original function. So my f of t is 331, plus that radical thing. And then I've got my linearization underneath. So we're going to take a look at the graph now near x equals 0. All right, and what we see, so here I am over x equals 0, way up here near 331.3, is I've got two curves that are kissing each other and are very, very close. And near the point x equals 0, you see they are nearly indistinguishable. So I'll zoom in. You can see how that red line is really sitting right on top of the green curve, and you can't really see it unless I zoom out a good amount on the x-axis. So hopefully you don't get dizzy here while I pinch out. And see, it's only really out here at the 40, 50, 60 away from t equals 0 that you start to see a difference. So there you can see now the better the shape of this radical function and how the red is really just a line that doesn't bend with it. But you can see the value of handing someone a model that's linear for values where something acts relatively linear, and then they don't have to worry about a square root. They can just, plug and chug to get to what they need and be within a desired level of accuracy. Okay, so hopefully that will translate to the field that you're worried about. Whether this be conservancy or engineering, physics, chemistry, all even economics, things like this. There's a wide array of applications for this type of work. Okay, and the second idea here in this topic while we're here is the notion of differentials. And I said this is kind of a hot topic in math. It was kind of the controversy of maybe about 50 years ago. Everyone's pretty much settled on it at this point. There's a few wackos out there, which I appreciate, standing their ground. But the idea that, dy dx for the notion of the derivative, this is considered to be notational, but there's also a way in which you can think of dy and dx as being numbers. And we do this a lot. And I'll show you kind of why that works. So what we see on the left is the definition of the derivative, right? Dy dx is the same as f prime of x, the instantaneous rate of change. And previously, we've kind of just treated dy dx as this kind of just ratio notation. But if I were to consider dx to be a non-zero amount, right, because we know that we're not really dividing by 0, we got around that with limits, then what I could do is multiply both sides by dx on this equation and get that dy equals f prime times dx. And this is what we call the differential form of this equation. And so you might be asking, like, how does that make sense, or why do we care? Well, just a brief graphical explanation on how we can tell that these two things are actually numbers would be to look at some function f of x. Let's say it's doing this. And again, I'm at some point a. X equals a. And I have a tangent line that's doing something like this. Try to be clear here. So here's my, tangent line L. It has the slope of the tangent line at this point, x equals a. And what we see is that, and this is my height f of a. If I carry this level through out here to some value x, so now this is out to some general value x that we'd measure past the point a. Well, what do I have here? I have the actual value f of x for that given x. And then these 2 points out here, a distance of x minus a away, this difference from the actual value of f of a to the point on the tangent line, this is what's given by dy, right? Because this is the slope of the tangent line over some dx. Whereas out here, this distance up to this point on the actual curve, this is what we call delta y, because that's the actual change in the value of the function from a to x. So you can see how, right, since dy dx is the slope of the tangent line, this dy is how much the L linear function increases over this little nudge in the input. So you can see how this is actually different than your delta y, or the change in the output. So delta y is really a number. Okay. Dy is really a number. It's a non-zero number for some nudge in the input, some very, very tiny nudge in the input. And so the reason that we care about this is because this gives us the best approximation for how much the system is going to wiggle based on some moving from some point I care about. So whether this is stability in a building, or how many amps can I feed this component, or whatever it might be. It's giving us an idea of how much wiggle room there is, and it's the best approximation for the change. So how do we put this into practice? I'm going to give you a very simple example. Let's say that we're manufacturing cubes of side length 5 centimeters. We know that the slicer is accurate up to 0.1 centimeters in the slicing. Okay, so each dimension could be 0.1 centimeters off, which is not too bad, right, out of 5. So the question is, how accurate will the volume be? Or you could also ask, what is the relative error in the volume? We might say a relative expected error. So we know that the volume for this cube would be given by x cubed, right? So if it's at 5, this would be, not 25. Did I say 25? 125 centimeters cubed should be our perfect cube. But the question is, how far off would we be if we were off a dimension of 0.1 centimeters and slicing these cubes up. Right, so in any of these directions, these could be off or wiggle by 0.1 centimeters, right, when the blade's coming down. So we take a look at the instantaneous rate of change. dv dx we know would be 3x squared. But if we moved this into differential form, meaning multiply both sides by dx, that nudge in the input, we'd get 3x squared dx. And so here what we're saying is that that nudge in the input, that dx, that error, is this 0.1, right? This is my dx. That's how off we could, expect the input to be, and we want to see what type of change that produces in the volume. So we'll get the resultant change over here. So we'll see this is really 3x squared times 0.1 centimeters, and we know that we're at 5 centimeters in dimension. And so what we get is what? 25 times 3 is 75 times 0.1 is 7.5. Centimeters cubed would be the dimensions here. And so we see that possible change in the volume would be 7.5 centimeters cubed. Okay, so there's a few ways to interpret this, and one would be, well, if our desired volume is 125 centimeters cubed, because that's 5 cubed, right? We know that this is really going to be bouncing between 7.5 more, which is 132.5 centimeters cubed, and beneath that, 117.5 centimeters cubed. Anywhere in between is where our volume could land, right? This is our approximation for the total error. It's a big range if you think about it. But again, any one of these dimensions or all three could be off by that little amount, and then that amount gets cubed. So you can see the drastic effects it can have just because of multiplication. Another way to think about this, so you can think about the range of possible outputs, or you can think about the fact that 7.5 out of 125 centimeters cubed is going to give you 0.06, which tells you that you've really got like 6% error in the volume possible from the input, the slicing being 0.1 centimeters off. So depending on the context, the question, these are different ways to talk about the error. You can talk about the flat rate between the two, or you can talk about percentage, because sometimes, right, flat rates or just talking directly about the values, the absolute error doesn't really paint a picture as much as a percentage might, and vice versa. Sometimes a percentage isn't appropriate, and you really want to be talking about, absolute value, dollars, centimeters, whatever it might be. So this is the main application from differentials that I'd want us to see. This is where they come from. And again, a bit of a weird idea, because can you really have an infinitely small number? We're kind of saying, yes, we can, as long as we define them in this way. And we can use them in predicting error like we did here. So I hope this is fun and exciting, and we'll see you in discourse for any questions you have on your practice problems. Enjoy.